Hello students. I'd like to work through two example problems that will illustrate how to convert from one concentration expression like molarity to mole fraction, to molality, to mass percent, to normality. We really take the guide of what we're given, and you are usually asked for the certain concentration expressions in an order that will streamline solving for all the things that you're being asked for. Okay, so we are given 1 gram of our solute, and we are given the mass of the solvent. And then we're told that the volume entirely of the solution is 101 milliliters. Okay, we're first asked for molarity, which would be mole of solute per liter of solution. So we're given in mils, but just converting that to liters. We'll then have to convert our 1 gram of our solute to moles, and using the formula mass, 46.07 grams in every 1 mole of our ethanol, with sig figs 0.0217 moles of our ethanol. Okay, so that'll simply go here, being careful of significant figures, of course, and our molarity 0.215 molar C2H5OH. All right, so we've satisfied one of the things that we were looking for. All right, next, mass percent, which would be the mass of the solute over the mass of the entire solution. So we're given 1 gram of the solute divided by 1 gram of the solute plus 100 grams of the solvent, so collectively 101 grams completely of the solution, times 100, and that gives us 0.990% of our ethanol, which would be most appropriate to show the chemical formula. All right, 2 things down. Mole fraction. Now, unless otherwise stated, we would definitely assume the mole fraction is in terms of our solute. So, how nice, we've already found 0.0217 mole of our ethanol, and be very careful because we need to divide by the mole of ethanol plus the mole of our solvent. So what we'll have to do is convert ourselves from 100 grams of water to moles of water. And this is 5.549 moles of H2O. And the mole fraction in terms of our solute, 0.00390. And remember that there is not any unit on that. It's simply a numerical ratio. All right, one more thing, molality, which is mole of solute per kilogram of solvent. So again, using the moles of our ethanol divided by kilogram of solvent. And we need to be careful. Molarity and molality are not the same concentration expressions. However, they can be similar in value when they are dilute, when our solute is of a small quantity, because that'll really then bring, if water's our solvent, the kilogram value to be very close to the liter value. And when we're dividing this, we get 0.217 molal of our C2H5OH. So we have found the molarity, the mass percent, the mole fraction, and the molality. Okay, that's all that we were asked for in the first example. With the second example, We're given an automobile battery that's 3.75 automobile battery that's 3.75 molar in sulfuric acid. And we're given the density of the solution. We need to be very, very careful when we're given densities that we interpret them properly. Then we're asked for these different expressions. All right, so where can we go from here? And remembering this is of the solution. All right, well, the first thing we're asked for is mass percent. So we're going to have to take a leap of faith and make an assumption. We're going to have to directly expand and literally interpret 3.75 molar sulfuric acid to be 3.75 moles of H2SO4 for every 1 liter of solution. So this is what we're going to assume. We're going to assume we have 3.75 moles and 1 liter of solution. So then, to get the mass percent, we'll need the mass of our solute, which then, if we convert 3.75 moles of H2SO4 to grams, and for every 1 mole of H2SO4, it is 98.09 grams. And so that is 368 grams of H2SO4. Now, if we have 1 liter of solution, and for every 1 liter is 1,000 mils of solution, and here's where our density comes in. Every 1 mil of the solution, we're saying is 1.230 grams of the solution. So this gives me, with sig figs, 1230 grams of my solution. So I know I have 368 grams of the H2SO4. Well, for mass percent, I'll divide that out by 1230 grams of my solution. And the percent by mass is 29.9% H2SO4. All right, so we directly expanded from the given molarity. We used density to get mass percent. All right, the next thing we're asked for is molality, which is the mole of our solute per kilogram of solvent. Well, all that we found is the mass of our solute and the entire mass of the solution. Well, the difference between these will be the mass of the solvent, and that's what I need there. So if I take my 1230 grams of my solution, which is my solute and solvent, subtracting away the mass of my solute, then we get, be careful with sig figs, I am only allowed to report with significance to the tens place, so we will get 860 grams of water, which would be 0.860 kilograms of solvent. And so doing that, we get a molality of, oh heavens, I'm not allowed to keep that 0 there for sig figs. So I can only report 2 sig figs. There we go. In converting, it's 4.4 molal H2SO4. One more thing, normality. In H2SO4, there are 2 equivalents for every 1 mole. 2 hydrogen ions are created for every 1 mole of H2SO4. So if I am continuing with the assumption that I have 3.75 moles of H2SO4, and for every 1 mole of H2SO4, there are 2 equivalents, and I'm running with the assumption of 1 liter of solution, well then it will be a normality of 7.50 normal H2SO4. For further examples, I have these problems, and here is the work to follow. As always, you can email any questions my way, or of course see me in class.